Hello. So we've just finished looking at the method of characteristics and how you can use it to solve the simple advection equation. So we want to move on now to the finite difference approach to the advection equation, and we'll look at some simple schemes, some simple explicit schemes that you can actually use to solve this equation numerically. Okay, just setting my time here. Okay, so so here is the model equation: du dt plus c du dx is equal to 0. The initial condition is given by this. Now we've seen that this has a general solution, which is equal to u naught x minus ct, and describes a wave that is traveling with a speed c. To the right if c is positive, and to the left if c is negative. So it's just a translation of a signal. Okay. Now in the case where c is positive, right, you have a signal moving from left to right. Now for each grid point j, such that for all nodes I less than j, this, for all such nodes we call this an upwind, and for the case where I is greater than j, we call that the downwind direction of the grid. I'll show you a picture of that very soon. Okay, so here, so if you have stuff moving from left to right, in this case as c is positive, then on this side right of j, we call this the upwind. If you want, you can imagine the wind is blowing from left to right, or whatever signal is moving from left to right. If you go up the wind, so you are here going against it, so that's upwind, and this is the downwind direction. Is the opposite in the case where c is negative and you have stuff moving from right to left. Okay, so you often hear these terms when dealing with hyperbolic equations. All right, so now to solve this numerically, I mean, one of the simplest things you can do is that you can discretize this using the first order forward in time scheme, right? That's easy. Now the special derivative, you can use a first order, you can use a forward first order scheme, you can use a backward scheme, or you can use a second order central scheme, right? Those are just simple schemes that you could try to use in order to solve this numerically. And so we are basically going to look at some of the advantages of these simple schemes and see whether they are useful. All right. So the forward scheme, basically the time derivative is given by this, in fact for all of them. And then for the forward forward in space, this is how you discretize it, right? You have j plus 1 and minus uj all over delta x. So this is the forward scheme. The upwind scheme or the backward scheme is given by this, right? You have uj and then uj minus 1, okay, backward. And then you have the central scheme, which of course the first order central scheme is second order grid. Okay, so 7 and 8, right? The truncation error for 7 and 8 are just delta t and delta x, and that of the central scheme of course is delta t for the time derivative and delta x squared for the special derivative. Okay, so we want to first look at these simple schemes and just look at the stability of the schemes, whether they are any useful at all. All right, so let's take the forward scheme, that is special, this guy, right? The first order forward scheme in space, of course in time too. So we want to look at this and see how stable it is. So as usual, we do the Fourier analysis, plug this into the scheme, into 7. If you do that, you end up with lambda k is equal to 1 minus mu into e raised to the power I beta minus 1. You have this, which you can also rewrite as that. Okay, so of course mu is equal to c into delta t over delta x, which is called the CFL condition. CFL stands for current Friedrichs Lewis number, okay, by these guys who came out with this thing here, and beta is equal to k delta x. Well, as we saw in the parabolic case, you require stability if the absolute value of lambda here is less than or equal to 1. Okay, so you analyze this and see whether this is less than 1 or there are some conditions for which it to be less than 1, and then from there you can determine the stability. Because here, I mean, just by looking at this, you can really see that this is not going to be stable, right? You have one mu there is positive, mu is positive. This is basically a positive quantity which is 1 or less than 1, right? E to the I beta is basically cosine of beta plus I sine. So I mean, you can just, but we're going to use a graphical approach. All right, this is a complex quantity, right? So what you can do is that we can plot this, right? If this is complex, then the absolute value of the complex number less than or equal to 1 means you are talking about the region within the circle of radius 1. Okay, and then you can do that for this as well. You can basically split the real and imaginary parts of this and then plot it. So if you plot this condition, you get whatever is inside this big circle. Okay. Now, if you plot the other guy, this guy here, equation 12. If you plot equation 12, right, using mu cos 0.5, this is what you get. The circle is outside the region of stability. All right, which means that this guy is not less than, the absolute value of this guy is not less than or equal to 1. Well, it can be equal to 1, but it's not less than 1. So it's not stable. Right, so this is one way of being able to tell whether the scheme will be stable. So sometimes you can use graphical conditions approach like this to determine that. But of course, in the limitations, right, we use mu equals 0.5. You can try mu is equals to 0.7 or 0.8. You will find that the circle will always lie outside this circle of stability or region of stability. Okay, all right, so from this we can conclude that because the absolute value of mu is not less than 1, it's not inside this region, that the scheme is unconditionally unstable, so it is basically useless. We cannot use the forward scheme. All right, the forward in time, forward in space scheme to solve the hyperbolic equation. Yes, the advection equation. And then you can look at the stability of the central scheme, right, as well. Right. So that's equation 9. You do the same thing by plugging this into the scheme, and then what you get is this. Again, straight away you can tell that mu will not going to be less than 1, right? It's going to be greater than 1. Perhaps equal to 1 at certain points where beta is equal to 0, right? But it's going to be greater than 1 for almost all the nodes, so the scheme is unstable as well. So both the forward in space and the central in space schemes are unstable, all right? So which means that we cannot really use them. Okay. So from what we've just discussed, we see that the forward in space and then the central schemes, we can't use them to solve the distance. So the next one to look at is the upwind scheme, which we'll look at next in our next video. But what you could try is, you see that I used a graphical approach, right, to show this. If you go to equation 12, I think, right, I use a graphical approach to show that this guy here is greater than 1 for the most part, and so it's not stable. So the question is, use a geometric approach that we've done before, right, to show that it's actually greater than or equal to 1. All right, so that is this exercise here which you can try. Okay, so the next one is look at the upwind scheme, which is the, if you like, the backward in space scheme. So we'll look at that next.